Right, so the rational numbers. Every natural number is also a whole number, which is to say that if n is an element of capital N, that implies that n is an element also of capital W. So just a bit of set theory notation here. If n is a natural number, that would imply that n is also a whole number. We may also write natural numbers are a subset of the whole numbers, which is to say that set of natural numbers is a subset of the whole numbers, right? So notation statement, and then a sort of reading out of that statement. Similarly, we might say that if W is a whole number, that would imply that W is an integer. And for those that are maybe unfamiliar, capital Z, boldface Z, is the standard indicator for the integers because the letter Z is the first letter in the German word for number, which is Zahl. Yeah? So that's how we get this symbol, capital Z, boldface, for the set of integers. All right, so let's introduce the notion of a rational number to characterize any number that is a ratio of two integers. So definition 6, set of rational numbers, Q. So m over n denotes rational numbers such that m and n are integers and n is not equal to 0. So that's the main idea here. All right, so definition 6, the set of rational numbers denoted by capital Q for quotient. M over n is a rational number such that m and n are integers where n does not equal 0. So we require the restriction n not equal 0 as division by 0 is meaningless or senseless, undefined. So the set a over b, quantity a plus 1 over b, and minus a over b contains ratios of integers, right? So it's a set of rational numbers. So these are all integers, respectively, and therefore we have a set of rational numbers. Arithmetically, we may consider integers like 6 elements of correlative sets of synonymous rational numbers. So this is a bit of fanciful language here that I've selected, but the idea should be rather perspicuous. Okay, should be rather clear. So what do I mean? So we may consider integers like 6, just integers in general, elements of correlative sets of synonymous rational numbers. So correlative sets, these correlate to each other. These correlate, in this case, the number 6. So they're synonyms of the number 6. But the main idea being these are all rational numbers, including the number 6. Because 6 may be expressed as any one of these, and in the most simple case, the ratio 6 over 1. And in principle, there are infinitely many representations of the integer 6. And if that's for some reason not the case, pretty sure it is the case, we'll explore maybe a proof, or at least a somewhat rigorous argument of that later on. But for all the number theorists out there, feel free to comment on in the comment section below what sort of formalizations of this idea there might be, that there are infinitely many representations of any given integer. All right, so the integer 6 is also a rational number. Generally, Note that the set of integers is a subset of the set of rational numbers. All right, moving along, any decimal that terminates is also a rational number. For instance, 0.01 may be expressed as the number 1, the integer 1, over 100, the integer 100. 0.101 may be expressed as 101 over the integer 1000, and the integer or the rational number, or the decimal number rather, 1.0001 may be expressed as the integer 10,000. Let's see what we have here. Yeah, 10,001 rather. May be expressed as the ratio or the rational number 10,001 over 10,000. So decimal transformations. To convert a terminating decimal to a fraction, count the number of decimal places, then write 1 followed by that number of zeros for the denominator. Okay, let's say that again. Decimal transformation. To convert a terminating decimal to a fraction, count the number of decimal places, and then write 1 followed by that number of zeros for the denominator. All right? So if we wanted to, and that's exactly what we've done up here, right, with each and every one of these. If we wanted to convert this decimal number to a fraction or rational number, what are we going to do? We're going to count the number of decimal places, 1, 2, 3, 4 decimal places. And in the denominator, we're going to write a 1 followed by that number of zeros for the denominator. 1, 2, 3, 4 zeros. All right, easy as that. Any decimal that repeats may also be expressed as the ratio of two integers. So terminating decimals, once again, may be expressed as the ratio of two integers. So what do we have here? We have 0.0 quantity 2, 1 repeating equals this expression here, subtended by an ellipses. The sequence of integers under the replica bar, I actually want to, let's see here, I want to pair this in terms of font and size and so on. So we've got Avenir Book, 10-point font, and the color gray. Avenir Book, 10-point font. What kind of gray is it? Let's have a look. Steel, great. All right, so the sequence of integers under the replica bar repeat indefinitely, and this is a term that I'm, maybe coining to some sense, but yeah, you might see it written as repeating bar, repeat bar. I settled on the term replica bar. In the case of 0.0 quantity 2, 1 repeating, there are 2 digits below the replica bar. Suppose we let x equal this number that we're considering here. Then we can write, by substitution, x equals this expression. Now, multiplying by 100, we'll move the decimal 2 places, multiplying both sides by 100. We'll move the decimal 2 places to the right. We get this expression here. Okay. And as we see, the decimal has in fact moved 2 places, 1, 2, to the right. If we align these two results and subtract, if we align these two results and subtract, meaning this guy goes under this guy, we obtain the following value. So 100 minus 100x minus 1x obviously equals 99x. And 2.12121 repeating minus this expression here leaves us with 99x equals 2.1. And then we can further simplify by dividing both sides by 99 to obtain this here rational expression, which is not yet a ratio of two integers. Okay? We can rectify this by multiplying both the numerator and denominator by 10. If we do that, x is unaffected. Okay, so whatever that evaluates to remains the same because we're doing arithmetically, right? Per the rules of arithmetic, we're applying this product to both the numerator and the denominator. So we get 21 over 990. Right, so this last result may be further reduced by dividing both the numerator and the denominator by 3. Okay, and that should be fairly intuitive. I mean, it's the smallest number that we can think of that divides both numerator and denominator. And then we should see that very quickly, right? So we get 7, obviously 21 divided by 3 is 7. It turns out that 990 divided by 3 equals 330. So we get 7 in the numerator and then 330 in the denominator. Okay, so dividing both numerator and denominator by 3 yields this final result, a ratio of two integers, and as such, a rational number. Great. So let's do another example. Show that 0.0 quantity 621 repeating. And I guess what I should have shown already, I want to actually go back because, yeah, let's actually clean up some of this MathML since probably won't have to do all of them, but yeah, I guess I will have to do all of them. Yeah, since we're doing MathML here, it's important that we get most of this right. And I should point out that even though these should really be MN tags, let's see why. Oh yeah, so the reason, oh yeah, okay, so I remember. So there's a reason why I'm doing MN tags, or mtext tags as opposed to MN tags. It has to do with the font rendering. Okay, so typically you would do, and this is later on when we're going to be doing all this MathML actually for being rendered, for rendering on a web browser. We'll be able to avoid this sort of silly thing. These should be MN tags. Okay, but the reason why I'm not doing it is because it's not giving me the font that I want. At least not exactly. Okay, so you can see the WebKit renderer here for pages is kind of being a little bit manipulative on the font. It's not a big deal, but it's just something to be aware of. And in fact, in this case of 1, I might not care that much, actually, so I might change these. I might change these around. But just something to be aware of. In fact, maybe we'll just go ahead and do that. For a good amount of them anyway. But I just want you to be aware that this is a sort of runtime bug, or, you know, it's a stylistic thing, more so than an actual bug, but something to be aware of anyway. And Fortunately, there isn't any simultaneous text highlighting in this editor like you would find in Xcode or VS Code, but no big deal. So there you go. Here we got a little bit of MathML to look at, and I probably won't do it everywhere in the following MathML scripts, but because, yeah, like I said, there's some font discrepancy that needs to be addressed, in my opinion. So that should be good enough. And then we can kind of just, yeah, you can see the difference here. It's purely aesthetic. Okay. All right. So we got that covered. And we have our result up to here. Okay. Again, the MathML involved here, and here's actually where we'll see a little bit more. You know, with the ones, it's not as dramatic, but with the number 2, you can start to see it is very much a different font. So this is Latin Modern Math that I'm trying to get, and this is just Times New Roman, I believe. So yeah, that's just not acceptable. So, but in order to get the overbar, just very quickly, so, and yeah, obviously with 0, you can see it mattered much less in terms of using the correct tag. So we got our leading digits, and then we put these guys here. Yeah, these 2 expressions inside the M over element with an accent over of false, which in theory should reduce this space, this padding. Okay, so this false should reduce this padding, but again, it depends on the rendering engine. Okay, to what extent these attributes actually render the way we want them to. So I know that in certain browsers, I'm pretty sure that Firefox is probably the most complete, MathML rendering engine. But it's very, very expressive, highly expressive, and renders quite a lot of attributes and expressions and so on. Safari has probably historically been the second best, and then there's been a great deal of effort. I'll talk more about this later on by a number of mathematicians, computer scientists, or programmers anyway, developers from the working group actually, that have pushed some updates to Chrome's rendering engine, which I believe is, well, it's not, is it blank? I'll have to come back and look and go over the particular rendering engines. But it's WebKit obviously for Safari, everything Safari related, and it is Gecko in the case of Firefox. And then I believe it's Blink for Chrome is the rendering engine for Chrome, and I believe Trojan is the rendering engine for Microsoft Explorer, certainly, and then might also be the one for Edge as well. So they all have different capacities, levels of capacity for what they're able to render. So let's just have a look here. So yeah, so that obviously does not affect the padding here, right? Just getting rid of it. And true also doesn't affect it either. So what we'll do is we'll have this false in there anyway, sort of indicating that we don't want padding here, but we'll deal with that. No big deal. Okay, so you get to see some MathML in terms of how I deal with the over bars. Okay, same deal here. And again, if I change this to mn, which is of course the actual, that would be the context markup. That would be important to get that right in terms of context markup. Since we're really just dealing with presentation markup here, right? So the serif, in terms of typography or calligraphy, is the concern on both of these. It's these serifs, right? We see that. Okay. All right, so let's look at this next example. So show that 0.06 quantity 621 is a rational number, meaning that it can be expressed as the ratio of two integers. In this case, we have 3 digits under the replicable bar. If we let x equal, and this would be the same solution, same strategy, same approach, same methodology for solving this problem. If we let x equal 0.0 replicable bar 621, then multiply by 1,000, right? Because we have 4 digits. We're in the thousandth. We're going to be dealing with the thousandth place here. Then multiply by 1,000. This will shift the decimal 3 places to the right. By subtraction and division, we have, okay, so step number 1, multiply by 1,000, shift the decimal place 3 positions to the right. Okay, we end up with this first expression, and of course our repeating digits. Okay. Yeah. So we're just going to subtract this guy from this guy. Okay. So we get 999x on the left-hand side, and we get 621 on the right-hand side. Very good. And we can right away reduce this integer to its simplest form. This rational number. Okay, this ratio of 2 integers to its simplest form. So if we now divide, and this is the way that this is the solution that the textbook offers. If we now divide the numerator and the denominator by 27, or alternately by 9 and 3, we see that, in fact, 0.0 quantity 621 equals 23 over 37, right? Now, the way I would approach reducing this kind of fraction is probably just recognizing, okay, both of these numbers, both of these integers, 621 and 999 respectively, are divisible by 3. That should be obvious looking at 621. 21 is divisible by 3, but really the rule is if you sum these 3 digits, you get a number that's divisible by 3, and therefore this number is divisible by 3. Right? 6 plus 2 is 8, plus 1 is 9. 9 is divisible by 3, so 621 is divisible by 3. And it's obvious that 999 is divisible by 3. But if that's not obvious, same deal. 9 plus 9 is 18, plus 9 is 27, which of course is divisible by 3. So how do we reduce this then? Well, let's just go to our calculator here and do 621 divided by 3, divided by 3, divided by 3, and that is the result that we get, which is no longer divisible by 3, so we reduce the numerator to 23. And let's just do the same exercise for 999. Divided by 3, divided by 3, divided by 3, right? So we can't go farther than 37. So one more time. Divided by 3, divided by 3, divided by 3. Okay, and so this is the smallest number that is divisible by 3 evenly, meaning without remainder. Okay, so 9, and so that's how we get our 37 down here. So we've just gone over two different ways for reducing this sort of fraction that might be not explicitly large numbers, but larger. So we have some very straightforward ways for reducing fractions of this size. As such, being the ratio of two integers, 0.0, quantity 621, repeating, is a rational number. Okay, and this little icon here, we'll use the diamond or losange character above to mark the conclusion of computation or calculation, which throughout this course I'll be referring to as, well, I'll be considering calculations and proofs synonymously. So computations are these sort of arithmetic procedures that we'll be carrying out, and then I'll consider sort of more algebraic calculations to be somewhat synonymous with proofs. And then proofs I'll be considering calculations throughout this program. So there you go. So we'll continue our discussion here of number types in the following sections.